So here in this particular video we are going to discuss about the third part of the equation of transfer. We are going to derive the differential equation which tells us about the changes in the intensity of radiation when it passes through the stellar atmosphere. And here I have shown it with the example. Let's say we have any of the cylindrical element in which there is a radiation, initial radiation, intensity of radiation I mu enters into this particular cylindrical element, but when it goes on through this particular cylindrical element and finally it reaches the end of this particular cylindrical element and escapes from this particular phase 2, the intensity of radiation become I dash mu. It means there is a change in the intensity of radiation. So how we are going to depict this in a mathematical form, we are going to see in this particular video. So first of all, we have to write out the first thing, which is the initial energy. So first thing is the initial energy. How we are going to write out of our intensity of radiation is equals to the I mu d sigma dt d omega d mu. So this is our initial, you can say that, energy, and the energy final is equals to the I mu plus di mu. It means there is a certain change in the intensity of radiation which we are going to represent as the di mu, and again d sigma dt d omega d mu. So this is our expression for the initial energy and the final energy. Now we know that in this particular cylindrical element or any of the stellar atmosphere, there is the change in the intensity due to the absorption of the energy, scattering of the energy, emission of the energy. So how we are going to write this into the mathematical form? So it's easy to write. We have discussed this in our previous video. So let's see how we are going to write this. So now the second part begins. We are going to write the energy due to absorption. So energy absorbed inside this particular cylindrical element or the stellar atmosphere, we can write it as minus I mu rho k mu ds d omega dt d sigma and finally d mu. So this is the energy absorbed. This is very, very important. The energy absorbed. Remember this particular equation. This is the energy absorbed. Now the second equation. This is our first. Then the second, which is the energy scattered. So energy scattered is also minus I mu sigma mu. So this sigma and this d sigma different. This d sigma mu is the scattering coefficient, and this d sigma is different and it's related with the surface element. Rho ds d omega dt d mu ds d phi dt and d mu. Okay, so all are there. So this is our expression, quite lengthy expression, so don't confuse it. This is I mu intensity of radiation, this is the scattering coefficient, this is rho density, this is the thickness, and this is per unit solid angle, per unit time, and per unit frequency. So this is absorption and this is scattering. Now we are going to use another equation which is very simple, like the final energy minus the initial energy is not equals to 0, because you all know that the intensity of radiation changes. So it means the energy final minus energy initial is equals to the energy that is absorbed plus the energy that is scattered plus the energy that is emitted. Let's say it's represented as E mu. Okay, so energy emitted. So this is the equation, and by plugging all of these equations, because the equation is quite lengthy, you have to do on your own to just plug in all of this particular equation of the E absorption, E scattering, of E emission, energy final and energy initial, what you are left is that I'm going to write out. So when you will solve this, by solving it, you will get this particular equation, which is d I mu is equals to negative of k mu plus sigma mu rho iv, first of all iv, rho ds I mu, one minute, here mu is a subscript, okay, so I mu, and finally here plus j mu rho, where I hope you all know that what the terms are. So I am going to recap that this is scattering coefficient, this is the absorption coefficient, this is the emission coefficient, and rest of the term you are familiar with what it is. Okay, now after rearranging this particular term, there is another equation which is d I mu by ds is equals to the negative of k mu plus sigma mu, mu means the frequency, okay, it's the subscript we are using here, so rho I mu plus j mu p rho. Here ds term is missing, okay, sorry for the ds term. So this is our wholesome equation which we are trying to derive, and this is your equation of transfer. This is your equation of transfer, where there are all of the three things which were the absorption, emission and the scattering of the radiation is happening, and this is our wholesome equation. That's why this derivation is not that much complex. You just have to write out the initial finite energy, the formula of the absorptions, all of that particular stuff, and just use some of the basics formula, and you can derive that particular formula of the equation of transfer. So now in the next few videos we are going to see the solution of this solutions. As you all know that I've also started the stellar dynamics, where I have the different types of the topics, like the gaseous states of the star and all that stuff. I am going to discuss this in the next few videos of the stellar dynamics. So this is for the today's video where I discuss about the equation of transfer. Its solutions will be in the next video. Solutions are quite complex and quite mathematical, but anyway we are going to cover the solution of also the equation of transfer. So thank you for watching my video.